Thank you. So, as a philosopher, what can I say about geometry? I would say that when I began to reflect on the topic, I was thinking that geometry is a science of space. But in fact, space is an object of study for philosophy as well as for geometry. And of course, in the philosophy of space, you've got several theses about space. For example, is space an objective entity? Is it a way of perceiving the world? If it is an objective entity, is it like a substance? Is it like a set of relationships between objects in space? So that's the famous debate between those with I don't know, those who defend the thesis that space is a substance, and those who defend the thesis that space is a set of relations, like Leibniz, of course. And of course, when you read these papers on the philosophy of space, there is no need to know geometry. It's completely different. But on the other side, we could say that space is the object of study of sciences, and especially of physics, of course, and of mathematics. So you could say that topology and geometry are sciences whose the object is a space. And usually I think people say that Euclidean geometry talk about figures in space, but modern mathematics, since let's say Frege's foundations of geometry, talked especially about space. Okay, so we've got this magnificent tree, this wonderful tree, but of course philosophy is also interesting not only in space, but in geometry itself. So there is a philosophy of geometry. And the philosophy of geometry may ask questions like, what are the methods used by geometers, and so on and so on. So the schema is complex. And of course, philosophy is also interested in results in theoretical physics. I mean, general theory, the Einstein's two theories of relativity have been very influential in the reflection for the reflection of philosophers on space. But one philosopher stands out because it seems to gather every aspect of this reflection, and this philosopher is Kant. Kant is interested in space. Kant is interested in the perception of space. So I didn't speak about psychology of space perception, but it's very interesting indeed. And of course, he's interested in geometry. And in fact, he makes connection between those different sides of our subject. And Kant, of course, I'm going very quickly here, says that there is an a priori sense of sensibility, of perception, and that this a priori science of experience of the world can be analyzed in such a way that we can dissociate what is the empirical content of our sensations and the forms of our perception or experience of the world, and space and time are considered by Kant ways of ordering of appearances, of empirical appearances in the world. And one of these ordering of appearances is precisely in space, is an object of a special science, which is geometry. So reflection on space and reflection on geometry are interrelated. And of course, you told us this morning, Max, Kant says that there is a fundamental opposition between the way the philosophers can speak about figures in space and the way geometers can speak about those figures in space or space itself. So I don't want to speak more about these topics. But the idea is that, in fact, the philosophical, the approach to space of figures in space by a philosopher, this approach is completely sterile. It doesn't produce anything interesting. While the approach to figures by the geometer is fertile and gives many interesting results. And the reason why is that, as Max explained this morning, the reason why is that the geometer constructs his figures in space. And there is a famous interpretation. The problem is the interpretation of this intuition, this use of construction by the geometer. There is a famous interpretation given by Intika, the Finnish philosopher, who says that in Kant you can find a procedure which is a classical procedure, which is an interpretation of classical procedure, which consists in the enunciation of the problem, of the geometrical problem, in exposition, ecthesis, in preparation, in the proof of in the giving of the solution of the problem. And
sorry. Point C.
Yeah.
Preparation is what Hintika says about Amoxcalli.
Yeah.
Because traditionally it's construction.
Yeah. So there is two aspects where construction does appear in ecstasis and in catastrophe. Anyway, okay. Here is the text, the famous text by Kant that you know very well since Max talked, since this morning when Max talked about it. So I don't want to pass too much time on it. The example taken by Kant is the Euclidean proof of the proposition 132, and the sum of the angles of a triangle is 180 degrees. And you know that in order to proceed, Kant says that you have to prolong the segment BC to CD and so on. So Friedman, in his book, makes two commentaries about this text. First, he says that the figure that is drawn is necessary to the proof itself. So the lines A, B, B, D, C, E are requirement to proceed completely and to give a complete proof for this theorem. And so I cite Friedman. I think the sentence is interesting. Geometrical proofs are themselves spatial objects. And he makes a second commentary saying that the lines which we use in the proof are drawn continuously and that we need time to do that. So time is also involved in geometrical proofs. So proofs proceed in time too. Time is a constitutive element of proof, as well as space. But I'm interested in space. Of course, Kant's approach to geometrical proofs and to mathematical proofs in general is rather unorthodox compared to the modern standards of the conception of a proof. In this modern and orthodox conception of the proof, we've got, I think, three important theses involved. The first one is a model thesis, which says that mathematical propositions, and especially the implications from axioms to theorems in geometry, so you've got axioms, and there is an implication to theorem, they are necessarily true, of course. It's not, they are not contingent. There is an epistemological thesis, mathematical propositions, and these implications, are a priori true. I don't need the experience to see the truth of those propositions. And the informational thesis, the idea is that mathematical propositions, and precisely, especially the implications from axioms to theorems, are analytical, either they don't bring new information. So in the modern acceptance of the proof, there is a general equivalence thesis, as I call it, between necessary, non a priori, and analytical, and of course, on the other side, between contingent truth known a posteriori, and synthetic proof. Of course, everybody knows that Kant said that necessary, the notion of necessity, the notion of knowledge a priori are equivalent, are co-extensional, I would say, but that there are judgments which are necessary a priori, but not analytical. But what interpretation should we give to this statement? That's the question. The question is, why did Kant conceive of geometry as a non-analytical process? And especially if you do think that the figures and prolongations of segments in the proofs which are given have not a simple function of a simple illustrative function. Yeah. So why do axioms and logic appear insufficient to understand what geometers do in giving their proof of theorems? And I think that there are two answers. I want to examine two answers. The first one says that we need to use construction in space because space is infinite, and I call it the geometric way to answer the question. And it corresponds to a sentence which is given by Kant in the beginning of the Critic of Pure Reason. In the transcendental aesthetic, space is represented as an infinite given magnitude. And there is a second answer, which I want to argue for, which says that it is because space is a singular whole, and I call it the metaphysical way. It is illustrated by the following phrases. One can only represent a single space, and if one speaks of many spaces, one understands by that only parts of one and the same unique space. And what I want to show is that in the two cases, the notion of a relation plays a crucial role. Anyway. So I'm going to begin with the first answer, which is in fact Friedman's answer. The fact that in geometry we use constructions is a consequence of the fact that infinite is present in geometry. So that's the part one of my talk. And the idea, which is proposed by Friedman, is that Kant's logic is restricted to the theory of syllogism, which means, in modern terms, that Kant knows only monadic first-order logic. Monadic first-order logic is a logic which uses only predicates and not relational terms, like to be blue, to be here, maybe, and so on. And the idea, I mean, it is true. It is well known that Kant said that logic was perfect. There is nothing to add to logic as it was when he wrote the Critic of Pure Reason. And this logic was the Aristotelian logic, which is monadic first-order logic, which means a logic without any relational predicates. But Friedman notices that every monadic first-order logic formula has finite models. And especially in a first-order logic without identity, a formula has, with k monadic predicate, P1, P2, P3, or PQR, as models with at most 2 to the k, to the power k individuals as models. Okay? And if you add to your first-order logic the logical predicate of identity, and you use different variables, x, y, a formula in this first-order logic with identity has only 2 to the k times n individuals as models. So, in a way, monadic first-order logic cannot grasp the infinite. So it's not possible. How to? I've give a simple illustration for that. Imagine that you, in your formula, you've got 3 predicates and 1 variable. So according to this theorem, you've got 8 possibilities of ordering the set of predicates. I explain. You have the possibility that no individual is P1, no individual is P2, no individual is P3. That's the first possibility. You have the possibility that an individual is P1, is P2, is P3. You've got a third possibility where an individual is P1, P2, but not P3, and so on. So we can give a simple illustration. Imagine that you've got 3 predicates: wise, funny, cyclists. You could distinguish individuals which are wise, funny, and who are wise, funny, and cyclists, individuals who are wise and funny but not cyclists, and so on and so on. So there is 8 possibilities. And in each case, the formula doesn't allow you to say that you've got an infinity of individuals. There is only, you can only interpret the formula as saying that there is a finite number of individuals. Or more exactly, there is always the possibility to interpret the formula as saying something true of only a finite number of individuals. Okay. Of course, if you add identity, you could say that an individual is P1, an individual X is P1, an individual Y is P12, and that X is different from Y. So you can give a greater number of individuals, you can distinguish a greater number of individuals. But the number of sub-formula which says that Y is different from X and Y is different from Z is finite. So the models are finite. Okay, that's an interesting theorem that you can give a proof of this theorem in elementary logic. But it is not so well known. But the problem is that geometric proofs need an infinite number of individuals, points, lines, and so on. And so monadic predicate logic suffers from an insurmountable limitation in the language of monadic predicate logic, you cannot have as objects which are constituted by an infinite number of elements. And so geometric reasoning cannot be made in the frame of monadic predicate logic. It is not possible. Okay. One of the most famous example is the faulty, according to modern standards, demonstration of the proposition 1.1 in Euclid, when he presupposes that the circles, the two circles, C1 and C2, intersect, but there is no proof of that, and you need a proof of that. You need a proof of the continuity of the circles. And of course, these limitations of Euclid approach to geometry has been surmounted by modern geometry, and the reason why is that modern geometry uses polyadic logic, which means that you add to monadic predicate logic relational predicates. And when you that's the first point. And the second point is that the modern polyadic logic uses nested quantification. It means that you can have a universal quantifier which is followed by an existential quantifier, or the converse. But it's very important because with the introduction of relational predicates, you can express logically models which are necessarily infinite. So there exist formulas whose models are only infinite. They admit only infinite models, infinite number of individuals. An obvious example is Hilbert's axiom of denseness in his book Foundations of Geometry. For all x, there exists y, such as x is smaller than y, and so on. And the idea is that between two elements, x and y, there is another one, z. Okay, z. And this formula has only infinite models. So in modern logic, you can, in modern time, I would say, after Frege reinvented the logic of quantification, with relational predicates, you can express formula with only infinite models. So that's very important. By the way, if you add to your predicates, monadic predicates, only one relational predicate, your logic can express infinite models. So that's very important, only one. And there is a famous theorem which says that monadic logic is decidable, for example. But if you add one relational predicate, the logic becomes not decidable, undecidable. That's a very impressive result. But the question is, what if geometric proofs need actually an infinite number of individuals, points of lines, but you have not at your disposal polyadic logic? How do you proceed? And the idea, which is Friedman's idea, is the idea that you need construction. Construction is the way to surmount the fact that Kant's logic is monadic predicate logic. Okay? And we can say that for Kant, you need to replace chains of logical deduction with a set of operations which allows you to generate points or lines indefinitely. Okay? And this indefinite iterability of constructive processes, for example, bisecting a line, guarantees the existence of the infinitely many points on the line, and for example, the denseness of line segments. And in his examples, it is rather easy to see that Kant uses three types of operations to produce dense objects. First, drawing a line segment connecting two given points. Then extending a line segment by any given line segment, as in the proof of the famous theorem, and drawing a circle, of course, with any given point as center and any given line segments as radius. That's the three procedures Kant gave in the Critic of Pure Reason. And, of course, you notice immediately that they correspond to the three first postulates of Euclid's element. I cite them here, but you know them by heart, I would say. So what is the conclusion? The conclusion is that grasping infinite divisibility or denseness, for example, for continuous property of lines is much more complicated, but it's a question of nested quantifiers. It's the same idea, but a little bit more complicated. So grasping infinite divisibility is not understanding a formula. For Kant, I mean, understanding a formula or sentence which says, as it is the case in Hilbert's presentation of geometry, which says that there is a dense number of elements, but it consists in the capacity to generate indefinitely the elements. And so in a way, the procedure is itself dense. That is the procedure which is dense. It is not given in a formula which says that there is a dense number of individuals. There is a consequence of this conclusion. In the classical interpretation of the synthetic character of geometrical propositions, many people say that the explanation of the syntheticity of theorems is due to the following facts. First, axioms, there is an S, are synthetic, are not analytical, but the inference from axioms to theorems is completely analytical and logical. But since the axioms are synthetic, the theorems are synthetic. That's a classical interpretation of the syntheticity of theorems in geometry. The existence of non-Euclidean geometries in the 19th century gives support to this interpretation. The idea is that, in fact, the syntheticity of the axioms allows us to say that such axioms is true, but other axioms are true maybe, axioms of hyperbolic geometry, maybe other axioms are true, spherical geometry, but the idea is that you accept a set of axioms, but then the process is purely analytical and the theorem is synthetic because of that, you know. That's the classical interpretation of the syntheticity of theorems in geometry, and maybe it was a classical interpretation of Kant's affirmation of the syntheticity of theorems. But what happens if we take seriously the fact that geometrical reasoning is procedural? It consists in iterable procedures to generate point indefinitely. The idea is completely different. the idea of the syntheticity of theorems is completely different. The idea is that axioms may be synthetic, but inferences are synthetic. And that's why theorems are synthetic. Maybe you could even add that, it would be bold, that axioms are analytic. I don't care. But theorems will be synthetic because of the procedures used in the proof. Okay. One of the consequences of this affirmation is that non-Euclidean geometries are impossible in this model, because the process of constructing and so proving the theorems is itself Euclidean. So you cannot have axioms, a logical deduction, and then theorems with a which would describe a non-Euclidean geometry, because axioms would be the axioms of a non-Euclidean geometry. Of course, it is the case in the first interpretation, but in this interpretation, which is Friedman's interpretation, it is impossible that there exists non-Euclidean geometry. One of the evidences of that is this following text by Kant. Thus, in the concept of a figure that is enclosed between two straight lines, there is no contradiction, for the concepts of two straight lines and their intersection contain no negation of a figure. Rather, the impossibility rests not on the concept in itself, but on its construction in space, on the conditions of space and its determinations. It's a very famous text by Kant. So Kant says that
They can discover non-Euclidean geometry from this.
Kant says that non-Euclidean geometries are impossible. Are impossible because when you try to construct straight lines, for example, you have to conform to the postulate that the straight line is indefinitely extendable, and for example, this figure doesn't make any sense. Okay, it will be an interpretation of the idea of straight lines by geodesics on a sphere, but it does not make any sense. Not because straight lines are forbidden in the axioms, but because the way we construct proofs are inherent to the procedures themselves. Okay. By the way, it seems to me that Poincaré claims exactly the same thing. Of course, you could say that Poincaré wrote famously that you could describe physical space by different geometries. And of course, after the invention of non-Euclidean geometries, Poincaré is perfectly aware of the fact that there exist different geometries. But which geometries exactly? When you read Poincaré, you realize that, of course, he admits a parabolic geometry, spherical geometry, and Euclidean geometry. But why does he admit those three geometries? Because he says it belongs to the concept of geometry that you can have a rigid world which move freely in space without deformation. And there is a famous theorem which says that if you admit that a space is such that in it roads move freely without deformation, there can be only three geometries: hyperbolic geometry, Euclidean geometry, spherical geometry. And Poincaré says the Riemannian geometry with variable curvature is not geometry. It's completely analytical. It's not real geometry. So it means that what is possible is determined by a specific construction, admissibility of type of constructions of what is possible in space, the free mobility of rigid roads, in a way.
I do not understand the consequence. What is the consequence of the first?
What?
Why the second follow from the first?
The second.
And why is for the fact that there is only two geometry that satisfy this constraint, making Riemann geometry not a real geometry?
Why Riemann geometry is not real geometry? Yeah, because our concept of geometry is derived from movements in space. Movements in space implies that you can see an object from different point of view, in presupposing that there is no deformation during the movement, and the idea which is presented by Poincaré says that you have to presuppose that the notion of space is constituted by these presuppositions. And in this case, you've got only three possibilities. In a curved space-time, there is no possibility of moving rigid roads without deformation.
No, you need you have a space that
I mean, when the space changes at each point of space. Of course, in variable curved space. That's what I call Riemann geometry. I mean,
which has no constant curvature.
Absolutely. Spaces have necessary constant curvatures for Poincaré. It doesn't admit spaces with variable curvature because of this condition which is imposed in what a space is.
Why Riemann geometry should admit the variable difference curvature? The curvature is constant in a sphere. Yes. So it's possible. Riemann geometry is perfectly possible. Yes. It's a real geometry, not a real geometry, it's a real geometry. Exactly because of that. Because sphere is a surface with constant curvature.
Yeah. Yes. But what we call Riemannian geometry is
in constant curvature. If I understand.
Yes, yeah. Of course, Riemannian geometry allows that there are space with constant curvature.
Yeah.
Of course, but the idea is much larger, and it means also that there are spaces with variable curvature. Okay. So, but the idea is the same as in Kant, in a way. Of course, the real possibility of a geometry is constrained by a kind of, by a condition on what a space is. So you cannot say there is logical possibility of all kinds of space, but we choose one. In fact, if spaces don't satisfy a certain condition of free mobility, it's not space. It's analytical, and it's not space. And so it's not geometry in a strict sense of the term geometry. So I wanted to talk about the notion of real definition by opposition to nominal definition, and the opposition between real possibility and logical possibility, but I'm going to pass that part of my talk. I jumped to the part 2 and to a critic of Friedman's approach to Kantian geometry. So let's remind that the idea proposed by Friedman is to say that the characteristic of space is the presence of an infinite number of individuals, and that this infinite number of individuals can only be produced by constructive procedures, and constructive procedures belongs to geometry. So, in fact, It's only geometry which can give you really space. So geometry constitutes space. That's, in a way, the thesis defended by Friedman. Is it true? I would like to do metaphysics a little bit. In Kant, you can say that space, spatial intuition, has three fundamental properties. Space is a singular entity. There is only one space. So in a way, space is a proper name. It's a proper name. I mean, space designates one entity. Okay. And there are only the infinite number of elements Friedman talks about are parts of this single entity. Right. Space is given immediately. That's the second property. And I'm going to argue that space has a third property, which is very important, which is the systematicity of this object. The singularity of space has been emphasized by Intikar a few years ago, and he defended the thesis that spatial intuitions mean simply individuality. So it means simply that in geometrical reasoning, we are obliged to pass from general propositions with quantifiers to propositions with constant or variables. And this passage is illustrated by the use of the rules of universal and existential instantiations in reasoning. But of course, Friedman has substantiated Intikar's point by claiming that the singular parts of space, because there is necessarily an infinite number of them, are produced by geometry. But the idea is the same. What is very important is the idea of singularity, singularities which are constitutive of the space and which are generated. But you can add another property to space, immediacy. The fact that the singular parts of the space, and it is an interpretation of Carson, which is a good connoisseur of Kant, the fact that singular parts of space are presupposed by geometry and not produced by geometry. Could say that the totality of space is given without being produced, but immediately, in a way. And in fact, there is a text by Kant, the following text, which says that there is a difference between geometry and arithmetic. In arithmetic, we generate numbers one after the other, and of course the procedure is indefinite. We can always generate another number. So in fact, there is a presence of infinity, but this infinity is completely different from the infinity which is characteristic of geometry, in a way. So about the object studied by geometry, because in this case, the totality of the points is given immediately, and parts of space appear only as delimitation of this object which is immediately given and not produced. Okay, I don't want to pass too much time on this interpretation, and I would like to add a third property. It seems to me that Kant's real problem is not the multiplicity, is not the problem of infinity. It's the problem of the fact that parts of space are given in such a way that they are indiscernible. All parts of space are identical in their property. So there is spatial homogeneity. And I think that's a fundamental problem in Kant concerning space. And it's very important because it is not possible to grasp the difference between 2 points of space by emphasizing intrinsic properties which would differentiate between these 2 points, because the properties are the same. So a conceptual apprehensions of those points is not possible. I cannot point to a property and say, well, this property allows me to say that this point in space is different from this other one. And I'm going to use a famous distinction by Russell between 2 kinds of relations. It's an old opposition, but which is very interesting. Russell distinguishes between internal relations and external relations. And in fact, this distinction is a new formulation and an old distinction made by Leibniz between relations of comparison and relations of connection, as Leibniz used to say. And what is the difference? The idea is the following. Relations of comparisons are such that those relations have their root, as the medieval philosophers used to say, in intrinsic properties of the objects which are related. For example, if I say that A is longer than B, it implies that A has an intrinsic property, for example, is 2 or 3 meters long, and B has another intrinsic property, independently of the property which is possessed by A. For example, B is 1 meter long, and that's the reason why, because A and B possess those 2 intrinsic properties which are independent from each other, that I can say that A is longer than B. So this kind of relation is very specific because it is grounded in monadic properties of the objects which are related to each other. All right? In the case of relations of connection or external relations, if I use the phrase, Russell's phrase, the idea is that the relation between the object, A and B, is not grounded on any intrinsic property. And I can give some example. The object A is near the object B. It's close to the object B. It's close to the object B. The event A is earlier than the event B, and the event A causes the event B. That's an example given by Leibniz, by the way. And the idea is, of course, that if I take an event and if I describe all the properties of this event, nothing in this description says that it is earlier than another event, of course. So the relation of being earlier than is not grounded, is not based on intrinsic properties of events. And that's the same for the points in space. There is an objection. We say, no, if I say that A is earlier than B, there is a property of A which distinguishes A from B. It is the fact that A occurs at this time and B occurs at this time. There are 2 different properties of A and B. And that's the reason why I can say that A can be for B. Okay. But what is interesting is that Russell has an answer to this objection, which is very interesting. He says that, of course, that's true, but to make this to attribute, to ascribe those 2 particular and different properties to A and B, I have to say that the date at which A occurs is earlier than the date at which B occurs. But between the dates, this relation is purely external because there is nothing in a date which differentiates this date from another one. So the events in time can be differentiated by the possession of intrinsic property which relates these events to two different dates, but the dates themselves, the moments themselves, have no difference in their intrinsic property. Is that the same thing for the objects in space? Of course, you can say that this object, the table, is near the wall, and of course you could say there is this relation because this table is here and the wall is here. But these intrinsic properties are given by the fact that there is a relationship between the places themselves. But between the places themselves, you cannot say that there is a difference which is due to the places. So the relation is purely external to, the spatial relation is purely external to. They have no intrinsic property at all, contrary to the objects which are in space. And I think that where there is a tight connection between the admission of external relations and the admission of a Pleiadic logic, in fact. The idea is that external relations are, and not relations of comparison, but external relations are irreducible to intrinsic properties. So you need necessarily relational predicates to express external relations, in fact. And in fact, Pleiadic logic is linked to this metaphysical thesis, I would say. At least some relational statements are reducible to monadic predication because we saw that relations of comparison were reducible to monadic predications. So, I would say that we don't need geometrical consideration to argue that description of spatial order is irreducible to monadic logic. Metaphysical considerations of the nature of space suffices. Now, there is something which is very strange, this idea that, the Russellian idea that this point in space is externally related to this other point in space. And the problem is that for Russell, you can imagine that if two objects are externally related, you can imagine also that one object does exist without the other. I can imagine that if I am the neighbor of another one, I can disappear, but the neighbor could continue to exist. The notion of external relations says precisely that the individuals which are related are completely independent from each other. But is it true of points in space or even events in time? I don't think so. And I'm going to end with texts from Wittgenstein, texts which are extracted from his conversation with the members of the Vienna Circle. And he says the following things. I distinguish totality and system. The books and chairs in this room are empirical totalities. Their extension depends on experience. Logical particles, numbers, points of space and time are systems. The second text is also interesting. It is necessary that the indications of a point in the space already contain the relations to the other points, which means that the relations between the points of the space are internal and not external. So, the idea exposed by Wittgenstein here is very simple indeed. The idea is that it doesn't make any sense to say that you've got one point. If you've got one point, you've got all the other points. And the comparison is with numbers. You cannot say that you've got only the number 2. if you've got the number 2, you've got the number 1 and the number 3 and all the numbers. And in fact, in a way, if we reflect on numbers, the idea is that a number is determined by the place relatively to other number. 2 is necessary between 1 and 3. Okay. So in fact, the idea is that there are a manifold of individuals which are not structured, but other manifolds are necessarily structured. And that's the case for the points in space, as it is for the moments in time. And that's what Wittgenstein called a system, or the systematic properties of such kinds of manifolds.
Speaking of time, almost over.
So, I will finish on that point. The idea is that points in space form a system as well. All points should be given at once, and we don't need the problem was not the opposition between monadic logic and polyadic logic, but rather the distinction between two kinds of polyadicity. Friedman says that the problem in Kant is the absence of polyadic logic. I don't think so. There is no problem in Kant. Kant completely understood that we need something other than simple polyadicity. We need polyadicity with internal relationships. And I will end by saying that there is a fair division of labor between the task of the philosopher and the task of the geometer. In a way, what I've just said, the distinction between two kinds of polyadicity, is the task of the philosopher, not the task of the geometer. And the task of the geometer is to investigate those kinds of polyadicity, those kind of specific polyadicity. Of course, it's not the task of the geometer to make the distinction. The distinction is presupposed by the geometer, but it's the task of the philosopher to make this distinction explicit and to show how on what geometry is grounded on. And that's precisely the point of view of the Kantian philosophy of geometry, I think. So.
Bueno, muchas gracias, Bruno. Pues empezamos un poco tarde, vamos a recorrer un poco el programa. Hay preguntas.
The first one concerning Kant. It seems to me that the problem about philosophy of geometry of Kant, I hope that Abel will not kill me now.
No, I can kill Friedman.
No, that's Friedman, okay, we can kill him right away. It's the same person.
But I don't like him.
I hate him very much as a person. But no problem. No, it seems to me that the problem is that Kant understands geometry as a science of space and use Euclid as a simplification of that. But Euclidean geometry is absolutely not a science of space. There is simply no space in Euclidean geometry. So if you try to understand Euclidean geometry or science of space, you cannot understand Euclidean geometry. That's impossible, simply impossible, because it's a completely different perspective. And by the way, Kant is in some sense one, not the only, but one of the origin or the idea that geometry is a science of space that was Kant larger, that certainly was not a pure point of view as Kant age. So I think that this is also a problem of Friedman interpretation, that it does not make this essential point. Right. The second is a very simple question. I quite confess it's my part, not good. I do not understand what are the two keys of polyadicity that we were speaking of, so I would like to.
Okay, so I completely agree on the first point with you. Of course, you're right. Friedman gives the impression that he wants Kant to be an interpreter of Euclidean geometry, with, in fact, he's not. such an interpreter. On the second point, what is the difference between the two types of relationship or polyadicity?
What are the kinds of polyadicity?
The term, the expression used by Wittgenstein is I think, very interesting. There are differences between numbers, for example, between 2 and 3, of course. Okay. But you cannot have this relationship without all the other relationships in a way. It's not the case for external relations between objects.
Axel, por favor.
I really like the talk, and even though I disagree in a lot of things, I like the way the pieces hang together. So I would push you into even a more round conclusion, because you left intuition on the side of your final conclusion. But it seems that you are suggesting that the idea that the reason why these earlier philosophers upheld to intuition was because they didn't have a way to account for external relations. But then it has nothing to do with individuals, and this is what another thing that Friedman is wrong about, right? Yeah, so I only wanted you to make explicit this conclusion that you think that intuition, if it is to do the work they want it to work, has to be intuition about external relations.
Yeah, that's a very difficult point. I have no answer to that. Yeah, I mean, when you, for example, if you read Wittgenstein, the conclusion is that points in space are not individuals.
Yes.
In fact, they are rather concepts which are internally related. They are possibility of placing an object here.
Yes.
And so in a way, it's conceptual. Space is conceptual in a way. And so, of course, it gives the impression that you lose something very important in space, is that you have the impression that you intuit elements of space. There is an intuition. It's not only conceptual. Yeah. And that's the difficulty, how to think about things which are internally related without transforming those things in concepts, in a way.
Brevemente, la última pregunta, bueno, que sea breve. Doctor Casanave. Perdón,
no.
Casanave.
No voy a estar.
Ah, bueno, ok.
No voy a estar.
Bueno, muchas gracias.